So let us now come to our first architecture for neural networks. This first architecture is called Perceptron, and we'll discuss that a little bit motivationally and also mathematically. So that architecture was introduced by Warren McCulloch and Walter Pitts in the 1940s. McCulloch is this older guy on the left part here, and Pitts is the guy in the middle. So McCulloch was a physicist, and no, McCulloch was a psychologist, and Pitts was a mathematician. And they wanted to make a model of the human brain, and they came up with this architecture, which we will give the name Perceptron. And then in the 1958s or 1950s, 1960s, Frank Rosenblatt analyzed this architecture more mathematically. So now let's look into that architecture. So this architecture consists of input units. They are denoted by x1 to xn, and we have an extra input unit, which we could call xm plus one, and it has it's fixed to some constant value. So x1 to xn are real numbers that could vary, but this extra input unit here has always a fixed value of 1. So these input units we also call input neurons. Now, when we have input units, we also need an output unit, and the output unit is called output neuron. It's denoted by this yellow circle here. So the inputs and the output are connected. They're connected by weights, W1 to Wn. The weights are also real numbers, and we have another weight for our constant input of 1, and this other weight we call B, and we also call that bias weight. So what we do is we sum up our inputs weighted by our weights W1 to Wn. So we take a sum, and we stay in the logic of this calculation by adding to this initial sum the value b, because b is just given by 1 multiplied by b. This gives the value b, so it would be the weight is b, and the input is 1. So adding this b here is totally conform with the logic of the calculation. So we call this a pre-activation. So our output neuron has a pre-activation. And the idea of McCulloch and Pitts was, as I said, they wanted to make a neuron. They wanted to make a model of the human brain. So what they had in mind is that the neurons in the human brains, they are connected, and if one looks at a certain given and specific unit, a neuron unit in the human brain, then they thought that this would fire or it would not fire. So it would have the value 1 or not, depending on its input. And the input is given by those neurons that connect to this specific output neuron, right? So we have some input neurons, and they connect to a specific other neuron. And depending on this input, weighted by given weights that specify the importance of certain inputs neurons for that output neuron, depending on that, this specific unit would fire or it would not fire. Okay. And then this firing function could be considered a nonlinearity. Well, it says, for example, if the input is above a certain threshold, let's say the threshold is 0.5 or 0.8, if this pre-activation exceeds that threshold, then the unit fires. So it's 1 or it's 0. So, and this is what this pre-activation, this activation function is doing. And this activation we call here sigma. Sigma stands, in our case, for activation function, or another term that you'll often hear in the literature is nonlinearity. And then from that we get an activation, and it could be 1 or 0, or it could also take other values depending on how this activation function looks like. Now, if we look at that mathematically, what we have is an input vector w given up here. This is lies in R to the n, and we have this this additional component of the weight vector, which we call b. We have a nonlinearity. This is our activation function. It maps a real number to a real number. So this is what we have given, so to speak. So this is inherent to the network. Now we have something that is given, so we also have something that comes into the network, which is our input. Our input, mathematically, we will treat that as a row vector. So this is x, and it lies in r to the 1 times n. So it's a row vector of size n, and we have this additional constant 1 that's coming in. So this is the input to our network. And then we have our output unit. Our output unit has an activation, and this activation, as I said, is given by a pre-activation, and this pre-activation is a linear term. It's x times w plus b, so that's a linear term. Like in components, it's wi times xi summed up and b added. And then on top of that linear term, we get a nonlinearity. So we have a linear term and a nonlinearity, which overall makes our network a mathematical function that is nonlinear. Yeah, and this, in terms of this dot here, this denotes a dot product. In German, Skalarprodukt. So if you see a bold dot, then this will denote a scalar product, a dot product, and the definition of a dot product is given here in terms of components. Now, for mathematical convenience, we can remove our b, our bias weight, remove that, and we also remove our constant input 1. I mean, this is just for mathematical ease. We're not changing anything. It's mathematically equivalent. We're just rewriting it so that it becomes more convenient. So we rewrite this b into our weight vector. So then our weight vector lies in r to the n plus 1. And we put our constant 1 also in the input vector, and we think of our input vector as having an additional 1 in the last component. Now, this is our model. Now we can split up the model in different parts, and these different parts are by what is given up here, at least the weight vector. We can characterize that as a parameter vector. And this is something that we want to learn, that we want to adjust, and that we want to estimate. I mean, there are different terms or names for this operation that we want to apply it to this weight vector, but they all mean the same thing. We want to adjust our weight vector so that it solves a certain task, so that our network, our perceptron, solves a certain task particularly well. Yeah, for example, we want to navigate a robot, so we learn this weight vector so that it's doing the right thing, or we want to classify a text, whether it's positive or negative, so we adjust our weight vector of our neural network so that the neural network is solving the task as good as possible. And then there's something that we cannot adjust in any case or in any way, and this is our input. So the input comes from the real world. This is our data. And in practice, we differentiate between training and test data, but that's not so important here. So this is our data. It comes from the real world. We cannot change it. And then the mathematical function itself. So what are we doing? We take the input x, so that's coming from the real world, and we put a mathematical operation on top of that. And this mathematical operation is given by multiplying our x with the weight vector w and then putting the nonlinearity there. So this can be rewritten as a function fw that operates on the input x, and this fw we call our model. Yeah, this is our maybe statistical model, and it's parameterized by some vector w. In neural network terminology, we often call it w. A little bit outside of neural networks, that's often denoted as theta. The parameters are often denoted as theta. And this our model. Well, in terms of the perceptron, it's a very simple model, but there are also more complex mathematical models that we'll see later on when we have more elaborate and more complicated, more complex neural networks. Good. So now the question is, what about this strange bias unit? Why do we need that at all? So the basic idea of that is we increase the capacity of our statistical model. So what does that mean? That means if we have this additional one, we have one additional parameter, and this is this b. This is one additional parameter of our model. So we have this mathematical model fw. Fw is given here. And now this Fw, this has one additional parameter, namely B. B is inside W. So with this, our model is more, well, it is richer. So you have an additional parameter that you can tune. So you potentially you can solve more tasks with that. You can solve more complicated tasks. So this additional weight element B it's just given to make our model richer. But in the future, we'll mostly ignore that. So we'll have to think of we have to keep in mind that this is actually there, but we'll not explicitly mention it. Good. So now when we have defined our neural network, the perceptron, and we can call it a function from r to the n plus 1 to r that has a specific form, like it has a linear part x times w, and then it has a nonlinearity on top of that. So this is our mathematical model. And now we consider the w as the parameters which we want to optimize. That's what I already said. And what do we have in practice? So what we have in practice, we have data. So we already had, I already mentioned this x as our input data. So now we do not only have one input set, one input vector, but we have multiple input vectors, like different points in a space. Like this could be different images or different sentences or different documents that we want to classify. And associated with each xi, so with each input xi is also a label, and this label yi. In the simplest case, that would be a real number. So it could be a 1 or a 0. This 1 or 0 could mean, well, this image is a cat, and well, you could code cats with zeros and dogs with 1. So this could be a 0 could mean that's a cat, a 1 would mean that's a dog, or 0 could mean that's a negative sentence or document, or this is a positive sentence or document. So we have labels associated with that. And what we want to solve then is we want to choose our weight vector w, which lies in r to the n plus 1. We want to choose our weight vector such that we minimize the sum of square distances. So our network outputs something given the input xj. So we have the input xj, where j ranges from 1 to n. We have this input, we have our w given, and these two components together make our perceptron, which is given by this function f here, make it output some real number. And we want to minimize the distance to the true label. So this is our true label. So we want to set our w such a distance to the true label is minimized. And in this way, we hope that our neural network, our perceptron, learns the problem that we have to solve. I mean, the problem is, given an input point, label this input point. Given this image, tell us if this is a cat or a dog. Given this document, tell us if this is about politics or if it's about sport. So we have this problem. I want that our network mimics the true label distribution, right? So it gives the correct answer for each input. So this is what we want to do in theory, at least. Now let's look at some perceptron learning algorithms. So we have our data, which we also call training data, and this training data consists of n points, xi, yi. We have a learning rate alpha, and we have initial parameter vector w. So this initial parameter vector w, this is just some initial guess of what could be a solution to the problem. Where do we get that from? I don't know. I mean, that if you could randomly initialize that, or you could set it to all zeros. This learning rate alpha, we will see that later on in later lectures. Basically, the idea of this alpha is we try to walk towards the optimal solution, right? So we have an iterative algorithm that is walking to the best solution that can solve the problem that we have, and this learning rate tells us how big steps we make in each iteration. So we take different baby steps, and this alpha says, do we take a very big step now, or do we take a small step? And now here's the algorithm. So what we would do is we choose some random sample t prime of size n prime. So we just take a subset of our training data, randomly chosen. In the worst case, that could just be one data point, so one xi paired with the label yi. And then we update our parameter vector. So we have the initial parameter vector, and we subtract something from that. And what we subtract is given here. So we sum over all our instances in t prime. So in the worst case, or in the extreme case, as I said, this could just be 1 point. So we go over this 1 point. We make this calculation here. So this is x times w. This is the dot product. And then we apply our nonlinearity. So this is just the perceptron, what a perceptron is calculating. We subtract from that the true label of the data point. So that data point x has a label y. And then we multiply that with something given by this term here. So this is sigma prime, this is the derivative. And the derivative is evaluated at this real number here, and then we multiply by x. So altogether, this is a real number, this is a real number, this is a real number, this is a vector. So this altogether, this gives a vector. We scale that vector by an alpha, and we subtract that from our current guess w. And then we update our w to become w prime. So we update our weight vector using this equation here. And then we have a new weight vector, and we continue, we just continue to do the same operation. We do that again and again and again. And we do it as long as some stopping criterion is met. Maybe the stopping criterion is we're running out of lifetime, or the stopping criterion could be we just set it to iteration 100 because that's long enough, because that's 2 days of computing or something. Or it could be we did not improve, so maybe we have some notion of improvement, and we know that with our previous weight vector we had about the same performance as with our current, and then maybe we decide to stop, right? So this is a perceptron learning algorithm that you will also implement in the exercises. So how do we derive at this? So this is like, it's a little bit like optimization in school. So we take the first derivatives, which is also called gradient. We set that to 0. So this is, if you want to optimize a function, you take the gradient, you set that gradient to 0, and then you calculate the optimal solution. And except that in this case, and what is our function that we want to optimize? So this is the function that we want to optimize, right? So imagine we take the first derivative of that function, and then we set it to 0, and then we solve for our w. So now the difference is we're not in school, so we're not in dimension 1, but we're in dimension n, or maybe n plus 1. So we are in a multidimensional space. And also an exact solution does not exist in general. In school, maybe sometimes you can write down the exact solution, but here the exact solution does not exist in general. Instead, we look at this gradient, so we calculate the gradient or the derivative, and we plug it into a general optimization technique that we call gradient descent, right? So, and this gradient descent we will get to know in 2 lectures. And on top of that, we do it a little bit stochastically. So we randomize this whole process. So this is given by choose a random sample. So we do it randomly, and doing it randomly sometimes has like empirically that often this is an empirical fact, like empirical finding that this often leads to faster to finding the good solution faster, or faster, or converging to the correct solution at all. So there may be different possible solutions that have different levels of goodness, and maybe to get to a very good solution, it is empirically seen often to work better if we have this randomization in the modeling process. And we'll see more on this in lectures 2 and especially also in lecture 3.